Next, my favorite kind of story in life is the kind that reminds us that we are nowhere near as close to as smart as we think we are. Well, that's the problem. The James Webb Space Telescope is upsetting the apple cart when Michio Kaku finally addressed the latest revelations from the James Webb Space Telescope. The scientific world held its breath. For weeks, astronomers and cosmologists had been poring over a mysterious new image captured by the telescope. An image that didn't just challenge existing models of the universe, but threatened to dismantle long-held assumptions about the formation of galaxies and the nature of time itself. Kaku, a theoretical physicist known for his work in string theory, and for making complex scientific ideas accessible to the public, had remained curiously silent while speculation grew. But now, with his voice entering the conversation, the depth of the telescope's discovery began to take on a new and astonishing clarity. Before we start, hit the like and subscribe buttons for more exclusive news. The image in question was not just another beautifully colored representation of the deep cosmos. It was something far more perplexing: an ancient galaxy, or what appeared to be one, situated at a distance so great that its light had taken over 13.5 billion years to reach. US. That alone was not necessarily surprising. What stunned scientists was the galaxy's size, structure, and level of maturity. According to current cosmological models, such a massive and organized system of stars should not exist at that early epoch in the universe's history. The prevailing Lambda CDM model, which serves as the backbone of modern cosmology, predicts a gradual evolution of cosmic structures. The further back we look, the more chaotic and unformed these structures should be. Yet here was a galaxy that looked fully developed: spiral arms, mature star populations, and even signs of a central bulge that typically takes billions of years to form. Kaku's commentary opened a gateway to deeper speculation, taking what had already shaken the foundations of cosmology and adding layers of theoretical depth. With his characteristic blend of imaginative insight and rigorous scientific grounding, he proposed that what we might be witnessing isn't just an anomalous galaxy, but potentially a crack in the very understanding of how time and space evolved in the early universe. The implications of this image suggest that either our understanding of the timeline of galaxy formation is fundamentally flawed, or that new physics, perhaps even new dimensions of reality, are at play. The James Webb Space Telescope, launched with the promise of peering deeper into the universe than ever before, had already dazzled scientists with its sensitivity and resolution. But this image represented something different: a confrontation with the boundaries of what the scientific community thought was knowable. Kaku described the finding not as an anomaly, but as a paradigm-shifting data point that could usher in a revolution in cosmology. The moment called to mind the upheavals brought about by Galileo's telescope or Edwin Hubble's realization that the universe was expanding. Just as those earlier discoveries expanded humanity's place in the cosmos, the Webb image seemed poised to reconfigure the very map of cosmic evolution. What makes this discovery particularly intriguing is how it challenges the temporal axis of cosmology. If mature galaxies existed mere hundreds of millions of years after the Big Bang, then the timeline of the universe's evolution must be reevaluated. Kaku raised the possibility that our understanding of time itself, especially in the context of early universal inflation and matter clustering, may be incomplete. According to some speculative theories, including facets of string theory and brain cosmology, the early universe may have undergone processes that rapidly accelerated the formation of large structures. These ideas, once considered fringe or purely mathematical curiosities, are now being brought into serious scientific conversations because of what Webb has shown. Kaku's reflections carried the weight of this cosmic uncertainty, suggesting that the universe may be far more complex and exotic than previously thought. The discovery may hint at unknown variables influencing the early universe: dark matter, behaving in unexpected ways, or even the existence of dark radiation or exotic particles that catalyze the rapid formation of massive galaxies. Some models posit that the universe is not homogeneous on large scales, as the cosmological principle suggests, but that it might harbor pockets of rapid evolution driven by localized conditions or ancient quantum fluctuations. If these phenomena are real, then the implications stretch far beyond astrophysics, challenging foundational assumptions in particle physics, quantum mechanics, and the nature of reality itself. One cannot underestimate the importance of visual evidence in such a scientific turning point. The image from Webb isn't just a dataset, it's a visual contradiction to the standard model. Where earlier telescopes offered hints or partial confirmations of early galactic structures, Webb has delivered clarity with such resolution and infrared sensitivity that the features of these ancient galaxies can be analyzed in unprecedented detail. Kaku pointed out that the telescope's ability to detect redshifted light with high fidelity is what makes this moment so transformative. For the first time, humanity is truly seeing the universe as it was at a time when it was supposedly still, in its chaotic infancy, and yet, what we are seeing looks eerily mature. This cosmic discrepancy invites fundamental questions. Is our understanding of redshift correct? Could some other process be mimicking the effects of extreme distance? While most astrophysicists maintain confidence in the redshift-distance relationship, Kaku entertained the idea that other, as yet undiscovered forces or quantum effects could be distorting our measurements. He emphasized that anomalies are rare. Science advances most dramatically not by ignoring them, but by grappling with their consequences. In his view, this single image may mark the first step into a deeper understanding of the universe, one that transcends the limitations of classical cosmology. The psychological effect of such a discovery also matters. Scientists, particularly those working within long-established models, may find it difficult to immediately absorb the implications of a finding that challenges so much. But, as history has shown, scientific revolutions often begin with discomfort. Kaku urged his colleagues to see this not as a failure of current theory, but as an opportunity and invitation to reimagine what's possible in light of compelling new data. The James Webb Space Telescope wasn't built to confirm what we already know. It was built to uncover the unknown. And with this image, it has delivered on that promise in stunning fashion. The implications of this discovery ripple outward into other fields as well. For example, theories of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, might need to be revised or expanded. If galaxies were able to form earlier and more rapidly than predicted, perhaps inflation created more structured seeds for matter to coalesce around. Alternatively, perhaps gravity behaved differently in the early universe, or other forces operated in conjunction to guide the rapid development of galaxies. Kaku has long been an advocate of multidimensional models of the universe, and this discovery gives fresh life to those possibilities. Another tantalizing possibility is that this galaxy and others like it may not even belong entirely to our universe. Kaku floated the idea speculative, but not without mathematical grounding, that the James Webb image could offer indirect evidence of interactions between our universe and other brains in a higher dimensional space. In this framework, collisions or interactions between brains could inject matter and energy into our universe, accelerating the formation of cosmic structures. Though radical, such ideas are gaining more attention as observations increasingly fail to align with classical expectations. From a technological standpoint, the achievement is also worth emphasizing. The James Webb Space Telescope represents the culmination of decades of engineering ingenuity, international cooperation, and scientific ambition. Its instruments are not just more powerful than those of the Hubble Space Telescope, they are a generational leap forward. The telescope's ability to see into the far infrared spectrum allows it to cut through cosmic dust and capture images of galaxies and stars at their birth. It allows scientists to analyze the chemical composition of these ancient systems, offering clues about the processes that govern their formation. And most importantly, it enables a kind of cosmic archaeology, reconstructing the earliest chapters of existence not through theory alone, but through direct observation. Kaku's discussion also underscored the philosophical dimensions of the discovery. If the universe is stranger and more complex than we imagined, what does that mean for our place within it? For centuries, humanity has been moving steadily away from the idea of being at the center of the cosmos. Each scientific advance has shown us a vaster, more indifferent universe. But the discovery of ancient mature galaxies may signal something different, not centrality, but connectedness. Perhaps the universe is not a singular event, but part of a larger, interconnected multiverse, and our understanding is only now catching up to that reality.